flag side of a transformer refers to the side that is connected to the primary source of power. It is typically the side with the higher voltage and lower current. In the situation of a 500 kV transformer, the flag side is the line side, which is connected to the power grid. The load side is connected to the electrical loads that consume the power. Regarding fault current calculation programs, there are several free options available besides Lotus 1.23 and Excel. Here are a few examples. Firstly, the National Fire Protection Association 7TE calculator, which is available online. Secondly, Schneider Electric Easy Power Essentials, which is a downloadable program. Thirdly, the Eaton Electrical Fault Current Calculator, also available online. These programs allow the input of transformer specifications, source voltage, and other parameters to calculate the short-circuit current of both the flag side and the load side of the transformer. Short-circuit current calculation is critical for electrical safety and equipment protection. It ensures that overcurrent protection devices, such as circuit breakers and fuses, can effectively interrupt fault currents before they cause damage or injury. Understanding the flag side of the transformer is also important for proper installation and operation. The line side must be connected to the power source, and the load side must be connected to the electrical loads. Reversing these connections can result in equipment damage or hazardous conditions. When using fault current calculation programs, it is important to input accurate data to obtain reliable results. This includes the transformer's kVA rating, impedance voltage ratio, and the source impedance of the power grid. Neglecting to input correct data may lead to underestimation or overestimation of fault currents, which can compromise the effectiveness of overcurrent protection devices. The National Fire Protection Association 7TE standard provides guidance on electrical safety in the workplace, including requirements for performing fault current calculations. The standard emphasizes the importance of qualified personnel conducting these calculations and using appropriate software and equipment. Schneider Electric Easy Power Essentials is a comprehensive power system analysis software that includes fault current calculation capabilities. It allows electrical engineers to model and analyze electrical systems, simulate fault conditions, and determine the appropriate size and settings for overcurrent protection devices. The Eaton Electrical Fault Current Calculator is a web-based tool that provides a simplified approach to fault current calculation. It is suitable for quick estimations and preliminary assessments. However, it may not be as accurate or comprehensive as more advanced software programs. When performing fault current calculations, it is essential to consider all potential fault locations in the electrical system. This includes faults at the transformer terminals, at the service entrance, and at various points throughout the distribution system. The fault current will vary depending on the location of the fault and the impedance of the circuit. The available fault current at a particular location in an electrical system is the maximum current that would flow if a short circuit occurred at that location. This value is used to determine the interrupting rating of overcurrent protection devices. The interrupting rating of a circuit breaker or fuse must be greater than or equal to the available fault current at the point of installation. If the interrupting rating is too low, the device may fail to interrupt the fault current, resulting in equipment damage or a fire hazard. In addition to calculating fault currents, it is also important to coordinate overcurrent protection devices to ensure that they operate selectively. This means that the device closest to the fault should trip first, while upstream devices remain closed. Selective coordination minimizes the extent of the outage and prevents unnecessary disruptions to the electrical system. There are several methods for coordinating overcurrent protection devices, including time current curves, coordination studies, and zone-selective interlocking. Time current curves show the operating characteristics of different overcurrent protection devices. Coordination studies involve analyzing the time current curves to determine the optimal settings for each device. Zone-selective interlocking is a technique that uses communication between overcurrent protection devices to improve coordination. Regular maintenance and testing of overcurrent protection devices are essential to ensure that they operate reliably. This includes visual inspections, functional testing, and calibration. Defective or improperly maintained overcurrent protection devices may fail to operate when needed, resulting in equipment damage or safety hazards. Short-circuit studies are crucial for electrical system design and safety. These studies involve calculating the magnitude of fault currents at various points in the system. The results of these studies are used to select appropriate overcurrent protection devices and to ensure that the electrical system is adequately protected against short circuits. There are several types of short circuits that can occur in an electrical system, including line-to-ground faults, line-to-line faults, and three-phase faults. A line-to-ground fault occurs when a conductor comes into contact with ground. A line-to-line fault occurs when two conductors come into contact with each other. A three-phase fault occurs when all three conductors in a three-phase system come into contact with each other. Three-phase faults are the most severe type of short circuit and can result in very high fault currents. The magnitude of the fault current depends on the impedance of the circuit and the voltage of the system. Higher voltage systems typically have higher fault currents. The impedance of the circuit includes the impedance of the conductors, transformers, and other electrical equipment. Lower impedance circuits have higher fault currents. The available fault current at a particular location in an electrical system is determined by the impedance of the circuit up to that point. This impedance includes the impedance of the utilities power grid, the service transformer, and the conductors and equipment within the building. The utility typically provides the available fault current at the service entrance. This information is needed to perform a short circuit study. The short circuit study should be performed by a qualified electrical engineer. The engineer will use specialized software to model the electrical system and calculate the fault currents. The results of the short circuit study will be used to select the appropriate overcurrent protection devices. The overcurrent protection devices must be able to interrupt the available fault current at their location. The overcurrent protection devices should also be coordinated to ensure that they operate selectively. Selective coordination means that the device closest to the fault will trip first, while upstream devices remain closed. This minimizes the extent of the outage and prevents unnecessary disruptions to the electrical system. The short circuit study should be updated whenever there are changes to the electrical system. This includes adding new equipment, modifying existing equipment, or changing the utility service. An outdated short circuit study can lead to incorrect overcurrent protection device selection and coordination. This can result in equipment damage, safety hazards, and unnecessary outages. The National Electrical Code (NEC) requires that short circuit studies be performed for certain electrical systems. The NEC also provides guidance on selecting and coordinating overcurrent protection devices. The NEC is a widely adopted code that provides minimum safety standards for electrical installations. Compliance with the NEC is essential for ensuring the safety of people and property. The Institute of Electrical and Electronics Engineers (IEE) also publishes standards related to short-circuit studies and overcurrent protection. These standards provide more detailed guidance than the NEC. The IEE standards are often used by electrical engineers in the design and analysis of electrical systems. Short-circuit studies are an important part of electrical safety. By calculating the magnitude of fault currents and selecting appropriate overcurrent protection devices, it is possible to minimize the risk of equipment damage, safety hazards, and unnecessary outages. Fault current limiters are devices that can be used to reduce the magnitude of fault currents. Fault current limiters can be used to protect electrical equipment from damage caused by high fault currents. There are several types of fault current limiters, including superconducting fault current limiters, solid-state fault current limiters, and magnetically controlled fault current limiters. Superconducting fault current limiters use superconducting materials to limit the fault current. Solid-state fault current limiters use semiconductor devices to limit the fault current. Magnetically controlled fault current limiters use magnetic fields to limit the fault current. Fault current limiters are typically used in high-voltage electrical systems. Arc flash is a dangerous phenomenon that can occur during a short circuit. An arc flash is an explosion of energy that can cause severe burns, blindness, and even death. Arc flash hazards can be reduced by performing arc flash studies. An arc flash study is an analysis of the electrical system to determine the potential arc flash hazards. The results of the arc flash study are used to develop an arc flash safety program. An arc flash safety program includes procedures for working safely on or near energized electrical equipment. The arc flash safety program should also include training for employees on the hazards of arc flash. Personal protective equipment (PPE) is required when working on or near energized electrical equipment. PPE includes items such as arc-rated clothing, gloves, and face shields. The level of PPE required depends on the potential arc flash hazard. The National Fire Protection Association 70E standard provides guidance on arc flash safety. The National Electrical Safety Code (NESC) also provides guidance on arc flash safety. Arc flash is a serious hazard that must be taken seriously. By performing arc flash studies, developing arc flash safety programs, and using PPE, it is possible to reduce the risk of arc flash injuries and fatalities. Electrical safety is a critical aspect of electrical engineering. By following safe work practices and using appropriate equipment, it is possible to minimize the risk of electrical hazards. It is important to be aware of the potential electrical hazards in the workplace and to take steps to protect yourself and others. Regular safety training is essential for all electrical workers. Safety training should cover topics such as electrical hazards, safe work practices, and the use of PPE. Electrical safety is everyone's responsibility. The NEC Table 310.16 specifies allowable ampacities of insulated conductors rated up to and including 2000 volts, 60 degrees Celsius through 90 degrees Celsius, in free air. This table is used to determine the appropriate conductor size for a given load. The ampacity of a conductor is the maximum current that the conductor can carry continuously without exceeding its temperature rating. The ampacity of a conductor depends on the size of the conductor, the insulation type, and the ambient temperature. It's vital to understand the concepts of voltage drop and its impact on electrical system performance. Voltage drop refers to the reduction in voltage that occurs along a conductor due to its impedance. Excessive voltage drop can cause equipment to malfunction, reduce efficiency, and even damage electrical components. The NEC recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. Voltage drop can be calculated using Ohm's law and considering the conductor's resistance and the current flowing through it. Factors influencing voltage drop include conductor length, conductor size, and the load current. Larger conductors and shorter runs will minimize voltage drop. Power factor correction is an important technique for improving electrical system efficiency and reducing energy costs. Power factor is a measure of how effectively electrical power is being used. A power factor of 1 indicates that all the power is being used effectively, while a power factor less than 1 indicates that some of the power is being wasted. Low power factor can result in increased current flow, high energy losses, and reduced system capacity. Power factor correction involves adding capacitors to the electrical system to compensate for the reactive power caused by inductive loads such as motors and transformers. Improving power factor can reduce energy costs, improve voltage regulation, and increase system capacity. Electrical grounding is a critical safety measure that protects people and equipment from electrical shock. Grounding provides a low impedance path for fault currents to flow back to the source, causing overcurrent protection devices to trip and de-energize the circuit. The grounding system consists of grounding electrodes, grounding conductors, and equipment grounding conductors. Grounding electrodes are typically metal rods or plates buried in the earth. Grounding conductors connect the grounding electrodes to the electrical system. Equipment grounding conductors connect the non-current carrying metal parts of electrical equipment to the grounding system. Proper grounding ensures that fault currents are safely conducted to ground, minimizing the risk of electrical shock. Bonding is the process of connecting all non-current carrying metal parts of an electrical system together to create a low impedance path for fault currents. Bonding helps to equalize the voltage potential between different metal parts, reducing the risk of electrical shock. Bonding is typically achieved using bonding jumpers or bonding conductors. Bonding is required by the NEC for all electrical systems. Surge protection devices, SPDs, are used to protect electrical equipment from voltage surges caused by lightning strikes, power line disturbances, and other events. Voltage surges can damage or destroy sensitive electronic equipment. SPD diverts surge currents to ground, protecting the equipment from overvoltage damage. SPD are typically installed at the service entrance and at sensitive electronic equipment. There are several types of SPD, including metal oxide varistors, silicon avalanche diodes, and gas discharge tubes. Each type of SPD has its own advantages and disadvantages. Proper SPD selection and installation are essential for effective surge protection.